Hello everyone, welcome to our exploration of the gateway aggregation design pattern. As designers, we always seek well-established and elegant solutions to common problems. Cloud design patterns are the solutions that enhance your application with proven methods for scalability, security, and cost efficiency in the cloud. In this video, we will discuss a problem, present the design pattern solution, and implement it in a real-life scenario. Whether you're a developer, an architect, or just someone curious to know about this design pattern, this video will provide you with valuable insights. My name is Madhur. Let's get started. Let's begin by setting the context and understanding the problem where you can apply this design pattern. When a client application needs to perform a single task, it may have to make multiple requests to different backend services. This means that an application that relies on many services to perform a task will have to use more resources for each request. Moreover, when new features or services are added to the application, more requests are needed, which further increases resource requirements and network calls. This constant communication between a client and the backend can negatively impact the performance and scalability of the application. This problem has become more common with the rise of microservice architectures, since applications built around multiple smaller services naturally have more cross-service calls. To address the problem at hand, we can implement the gateway aggregation design pattern. This pattern involves introducing a gateway that acts as an intermediary between the client and the backend services. The gateway receives client requests, dispatches them to the various backend systems, and then collects the results and sends them back to the client in a single response. This pattern can significantly reduce the number of requests that the application needs to make to the backend services, thereby improving application performance, especially over high latency networks. Now let's discuss some of the issues and considerations for this design pattern. First is single point of failure. The gateway service may introduce a single point of failure or a performance bottleneck. Ensure the gateway is properly designed to meet your application's availability requirements. Secondly, we need to handle failed services. If one or more service calls takes too long, it may be acceptable to time out and return a partial dataset. Consider how your application will handle this scenario. Third, implement correlation IDs. Implement distributed tracing using correlation IDs to track individual calls. This also helps simplify aggregation logic, as data returned using the same correlation ID can be clubbed together. Another consideration is to separate aggregation from the gateway. Instead of building aggregation into the gateway, consider placing an aggregation service behind the gateway. We should use this design pattern when a client needs to communicate with multiple backend services to perform an operation. This pattern is unsuitable if you want to reduce the number of calls between a client and a single service across multiple operations. Adding a batch operation to the service may be better in that scenario. Here is an example of how the gateway aggregation pattern can be implemented for an e-commerce application. Imagine you have an e-commerce website where users can browse products, add them to their carts, and check out. However, your backend services are divided into microservices for better maintainability and scalability. The challenge is that when a user views a product page, several backend calls are needed to display all the relevant information. For example, product services to fetch product details, inventory service to check stock availability, cart service to check if the product is already in the user's cart. These individual calls can lead to chattiness, as multiple calls to different services increase network traffic, and also complexity, as managing multiple APIs adds complexity to the client-side code. To solve this problem, we can introduce an API gateway to implement the gateway aggregation design pattern. With this, the user sends a single request to the API gateway for a specific product ID. The API gateway acts as an intermediary and can be implemented using Azure API Management if you are on Azure, or Amazon API Gateway if you are on AWS. The gateway manages the individual requests to the backend services. The response are then combined by a helper service. This can be implemented using Azure services such as functions or app services. On AWS, it can be implemented using Lambda or Elastic Beanstalk. The gateway then sends a single response back to the client application. With this, you get improved scalability and maintainability while simplifying client-side code by interacting with a single API endpoint. This is just one example. The gateway aggregation design pattern can be applied to various scenarios where a client application needs to interact with multiple backend services to complete a single task. If you found this video insightful, do share, like, and subscribe. Until next time, stay curious, stay data driven.